Hello and welcome back. Today we're going to talk about gradient fields a little more, and specifically we are going to explore their special role in computing line integrals. So let's investigate that connection between gradient fields and line integrals a little more. Let's say we have a gradient field with a potential and we also have a curve, and we want to integrate over that gradient field along the curve. What happens here? So consider a gradient field V, and let's say that maps from Rn to Rn with a potential, and that will be denoted by capital F. So capital F is a mapping from Rn to the real numbers R. And we'll also consider a curve. We call that gamma. And let's say gamma is defined on the interval alpha beta, and gamma maps, of course, to R to the n. We give the endpoints a name as well. So let's say A is the starting point of gamma, so that's gamma of alpha, and B is the endpoint of gamma, that's gamma of beta. Okay, so we know, because V is a gradient field and F is its potential, we know the gradient of F of x is equal to V of x for any x in R to the n. Now let's consider a function that evaluates that potential along the curve gamma. So consider the function, we call that small f, and we'll define small f of t as capital F of gamma of t. So we first put t into the curve, we get an n-dimensional point out of that, and then we put that into f and we get back a real number. Okay, so that is the restriction of capital F to the curve gamma. Then we know f is a function that maps the interval alpha beta to some real number. So the codomain is R. What we also know is something about the derivative of f. So we can compute the derivative of f with respect to t. We denote that by f dot of t, and we can just do this using chain rule. Small f is capital F of gamma of t, so the derivative is the derivative of the outer function, that is the Jacobian of capital F, evaluated at the point gamma of t, and then we need to multiply with the derivative of the inner function, and that is gamma dot of t. All right, and you'll notice that Jacobian, you do know that Jacobian is the same thing as the gradient transposed. So what we have here, in fact, is the gradient of f evaluated of gamma at gamma of t transposed times gamma dot of t. So this gradient is the same as the vector field V. So we can just say, well, that is V evaluated at gamma of t, V along the curve, basically, transposed gamma dot of t. And that in turn is the scalar product of v of gamma of t and gamma dot of t. Okay. Now that scalar product, that should look familiar if you have studied the previous videos, because that is an expression that appears in the integral over the vector field v along the curve gamma. That is precisely that expression here. So recall, the integral over gamma of v ds is, by definition, the integral from alpha to beta, the boundaries of the interval, of precisely that scalar product here, v of gamma of t and gamma dot of t dt. And we now know this scalar product is equal to the derivative of our one-dimensional function small f. So what we get here is, well, this is the same thing as the integral alpha to beta of f dot of t dt. And what that means in turn is, well, we integrate a derivative in dimension 1. That's easy. So the function is, of course, the antiderivative of its own derivative. So in other words, that integral is simply f of upper bound, f of beta, minus f of lower bound, f of alpha. And now remember, small f is defined as capital F after gamma. So we can rewrite that expression here as capital F of gamma of beta minus capital F of gamma of alpha. Or, in other words, capital F of B minus capital F of A. So what we can see here is two things. First, the result, the integral over this gradient field here along the curve gamma, does not really depend on the curve gamma at all. The result only depends on the points B and A. So what the curve does in between those 2 points is completely irrelevant. It's only the endpoints that matter. And the second thing that we can see is that capital F, this function here, acts as some kind of antiderivative to the gradient field f. And that kind of justifies what we did before. We call that a potential or an antiderivative, because that's exactly what it is. And you can see this even maps here, maps over to integration theory here. Okay, so that behaves in a very similar way as in one-dimensional integration the antiderivative will behave. So let's quickly note that this integral here, VDS along gamma, depends only on f and its values at the start endpoint of our curve gamma. And that, of course, is something that is highly usable because it makes integration a whole lot easier. So integrating over a gradient field becomes a whole lot easier than integrating over general vector fields if you actually have a potential. Yeah, okay, so you need to spend some time to compute that potential possibly, but that's it. So let's denote that in a little theorem. And we'll also specialize that to more or less arbitrary domains. So let's say we have a domain D, let D be a subset of R to the n. We want that to be open so that everything can be differentiated. Let's take a vector field V defined on that set D mapping to R to the n. That we want to be a continuous vector field. So that integration works out nicely on D. And we want a curve gamma. So gamma is defined on some interval alpha beta, maps to D, and we want that to be a continuously differentiable curve. Then if V is a gradient field, the integral along gamma over V can be computed by just evaluating the potential at start and end point. That's what the theorem says. So if V is a gradient field, then the value of the line integral over V along gamma ds, that value depends only on the start and end point of gamma. And it can be computed as integral over gamma VDS is the potential F of gamma of beta minus the potential F of gamma of alpha, where F d to R is a potential of our vector field V. And we call such an integral path independent. It only depends on start and end point and not on the path in between. Okay? So that's called path independent. And in particular, so note one more point, that also means if we have a closed curve, a curve where start and end point are equal, so like a circle, for example, then the integral along that path is always 0, because we evaluate capital F at the same point, so the difference needs to be 0 necessarily. So in particular, if gamma is a closed curve, meaning gamma of beta equals gamma of alpha, then this integral of VDS along gamma is 0. Okay, that kind of justifies the name for these vector fields, conservative. Basically what that means is that if you're moving through that field along any curve and get back to where you started, then you have not gained or lost any energy. Your energy state at that point is the same as when you started. At least not through the force of the vector field, yeah? So you moved in some direction, being pushed by the force of the vector field. You moved in some direction with the force of the vector field pushing against you. But in the end, the net gain is 0. So that justifies the name for that vector field as being a conservative vector field. Okay. Now, one question, of course, that remains is, can we easily find out whether a vector field is conservative or not? Maybe without actually computing the potential. As you have seen in the examples, that might be possible, but it might also be pretty hard to compute such a potential. So we might like to avoid that if we can. Especially in cases where we don't need it. So if we have a closed curve anyway, and we could be sure that the vector field is conservative, the integral would always be 0, so we don't need the potential in that case. And it would be nice to have a criterion for when a vector field is conservative. And that's something that we are going to talk about in one of the upcoming videos. I'll see you then.